Jesse. Today I'll be discussing some problems and open questions in AD with integrals. Some of this presentation is based on work with a number of collaborators, including Kevin, who's here somewhere. And this culminated in a SIGGRAPH paper a few years ago, and I'm currently doing some follow-up research in this area. My goal for this presentation is to motivate why AD with integrals is an important problem, and to discuss the current state of research in this area. And I'd love to hear about any related problems that any of you encounter in your research. All right, so we're all a big fan of gradient-based optimization. We've probably seen this before. And it's also super useful for physical simulations and graphics. And there are lots of gradient-based methods, LBFGS, Gauss-Newton, and all of these sort of iteratively update parameters, and they change the function output in order to minimize an objective. So one thing we might want to do is to produce an accurate simulation of the motion of a ball traveling between 2 points. And the parameters to optimize here are the control points of the trajectory, and we optimize for physically valid configurations by minimizing the Lagrangian energy integrated over time. In graphics, we often want to make some 2D image that either look photorealistic or to be stylized, for example, with a sepia filter. One way to generate images is to layer vector paths and then to estimate the color of each pixel by averaging over the color of the region it encloses. We might optimize the location and color of the layered paths in order to match a given image. One exciting direction is mixing graphics, physical simulations, and other things with deep learning to build these stronger reasoning capabilities. And an example is we can use a neural network as input to a rasterize, and then train the entire system end to end with gradient descent. However, this requires that we have access to the gradient of all of the components of the system. Computing the derivative of an arbitrary simulation is quite difficult, but what makes them challenging? So at least one thing that makes them challenging is that computations in both graphics and physics typically take the form of integrals over regions. As an example, a ray tracer constructs an image by integrating the color value over each pixel in order to produce a plausible image. In a similar manner, a finite element simulation aims to integrate quantities such as stress and strain over discretized regions of space. In trajectory optimization, the integral is over the 1D trajectory rather than a grid. There are, of course, many other applications that are characterized using integrals. But why does integration pose a challenge to automatic differentiation frameworks? To see why, consider the integral of a function composed of operations typically used in deep learning, like the sigmoid and dot product operators. When the function is continuously differentiable, the derivative of the integral is simply the integral of the derivative. This means that we can use traditional autodiff and get the correct answer. So discontinuities are prevalent in graphics as well. For example, in triangle rasterization, we represent a triangle by coloring a grid. At a high level, a rasterizer attempts to find the color of the occupied area in each pixel. It accomplishes this by testing whether points in the pixel lie in the intersection of half planes. More concretely, we test if the point is below line 1, to the right of line 2, and above line 3. This simple construction is widely used. Although differentiating integrals of discontinuous functions like this is challenging, there are a number of approaches to addressing it. We'll first show why sort of naively applying existing AD methods doesn't work well for this class of problems. We'll show a very simple example of the derivative with respect to t of an integral whose integrand is 1 if x is less than t and 0 otherwise. In order to ground the problem, we'll just compute this by hand analytically. So just from looking at the graph, we can see that if t is negative, we integrate over no mass. If t is between 0 and 1, the value of the function is 1 for a distance t. So the integral is t. And if t is greater than 1, then the value of the integral is 1. Computing the derivative with respect to t is quite easy. We just compute the derivative with respect to each part of this piecewise function. So the derivative of 0 is 0, t is 1, and 1 is 0. We may more compactly express this with our bracket notation. So in practice, we can't compute integrals analytically. We have to use numerical techniques like quadrature or Monte Carlo estimation. And thus, practitioners often write the integral as a for loop over samples, and then differentiate each of these samples. The derivative is 0. Why? Because the function is constant at each of these sample points. Unfortunately, this answer is incorrect. So while autodiff in general is correct almost everywhere, even for discontinuous functions, this implementation doesn't encode the semantics of the integral, and therefore gives the incorrect answer. So instead, one thing that we can do is introduce an integration primitive into our differentiable programming language. And the derivative of the step function is 0 everywhere except t, where it's infinity, at least intuitively. And we can represent this as the Dirac function of t minus x. So to recap, discretizing the integral in the derivative computation often gives the wrong answer. Introducing integration as a language primitive and carefully handling discontinuities produces correct answers. Let's quickly look at this in code just to hammer home the message. Discretizing involves iterating over the variable of integration and incrementing whenever x is less than t. The derivative just applies to the body of the conditional, so the answer is 0. It's necessary to have an integral primitive in order to write the code for the initial expression, and likewise for the derivative. Additionally, in our work, we use a Dirac delta to account for the discontinuities in the derivative. So all that remains, at least in this approach, is to eliminate this delta. And to do this, we first apply a change of coordinates that translates the delta. And only after that can we apply something called the sifting property to cancel out the delta and give the desired answer. For the sake of completeness, we have the math worked out. Don't worry about it. OK, so to recap, we first compute the derivative, introducing a delta term, then eliminate, producing the correct answer. And in our paper, Systematically Differentiating Parametric Discontinuities, we show how to generalize this approach to maybe some more interesting programs. OK, so now we're going to switch to talking a little bit more broadly about the research landscape. Where have we seen this problem pop up? And what have practitioners and programming languages researchers done to try to resolve these problems? So we're looking at 3 different approaches. The first is direct sampling. The second is approximation. And the third is analyzing correctness. So sort of the key technical idea of a lot of these approaches, which I'll just sort of pop by. Don't worry if you don't understand it. But the main idea is that when we take the derivative of an integral with some discontinuities, we end up with 2 terms in the derivative. There's an interior term, and there's a boundary term, where you can think of the boundary being the boundary of the discontinuities that occur in the integrand. All right, so in direct sampling, the main idea is just directly sample that boundary term. This requires some regularity of the boundary term so that you can sample the implicit surface specified by the discontinuities. Now, these approaches provide some strong guarantees, for example, unbiasedness. And they also tend to be pretty low variance. But they come with this, limitation on the functions you can express. what I'm calling approximate approaches blur this boundary term so that stochastic sampling of the interior captures the boundary contribution as well. These approaches often require some manual tuning to explore the trade-off between the amount of noise that you introduce and the convergence rate. However, they work on a broader class of functions. So, and then finally, I want to talk a little bit about some work from the programming languages community that talks about how to differentiate problems in probabilistic inference and to verify that they're correct. So this is sort of the other side, which is figuring out when things go wrong in some sort of automated way, as well as guaranteeing correctness, perhaps not in the case of parametric discontinuities. OK, so zooming in a little bit more to direct sampling, we can look at this approach called the edge sampling method. This is one of the first papers in this area. And the idea is to do triangle mesh rendering by directly sampling these triangle boundaries. Some concurrent work on the probabilistic inference side has a similar unbiased estimator. And they do some variational inference. The problem they look at, or one of them, is modeling a device like an air conditioner, the controller of an air conditioner, that tries to keep the temperature of a room within some specified bounds. They find that direct sampling performs better than other commonly used methods that you might try to solve this problem. Going to our work, TEG was the first, to our knowledge, to introduce integration as a language primitive to solve this problem. And it broadened the scope of direct sampling methods beyond affine discontinuities to invertible discontinuities. In this example, we optimize for a billiards trick shot and contrast it against the traditional autodiff approach. We see that ignoring delta terms leaves us with a trajectory that defies physics by changing velocity spontaneously. This stands in contrast to the clean trajectories in the former case. We study an idealized series of bungee cords that deform, and after deformation, a string prevents further extension of the spring. You can think of this as like the stress-strain curve of like a composite material or something like that. We jointly model the time and acceleration of a person connected to the string bungee system, and we optimize the spring constants and the lengths of the springs. The spring constants and lengths of the strings. And we add a hard constraint that the person doesn't hit the ground to prevent death. We find that the optimization of spring constants and string lengths using TEG works better than both finite differences and ignoring the contribution of the parametric discontinuities. Interestingly, accounting for parametric discontinuities makes the optimization landscape smoother and convergence is faster. So now let's take a look at some of these approximate solutions. The soft rasterizer paper smooths out the edges of triangles in a triangle mesh rendering problem and sort of avoids parametric discontinuities entirely by just changing the problem you're working with. And then you have this free parameter to tune, which is the amount that you blur, effectively. And in their application, the goal is to use a neural network to find a 3D mesh that renders to a given image. The warped area sampling paper lifts the boundary term into a term in the interior. It does this by constructing a function over the interior that matches along the boundary and interpolates in the interior. Notably, it constructs an unbiased estimate of the derivative, similar to the direct methods. This application depicts the derivative of some scene parameters. DVG computes the derivative of the color of a pixel with respect to the parameters of a spline in an image comprised of vectorized components. In these vector graphics pipelines, directly applying AD fails. DVG fixes this by blurring the lines in the image via convolution. The goal here in this application is to stylize a given photo by finding the closest vector graphics representation. So on the left is the original image, and on the right is the vector graphics image. Oh, the other way around. Anyways, and then some very recent work, A delta, effectively zooms into a discontinuity until it's approximately linear. I think of this technique as sort of an interesting mixture between finite differences and automatic differentiation that still gets you reverse mode. However, proving correctness is quite tricky, and they have sort of this approximate correctness guarantee. This also means that there's still some parameter to be tuned, in particular how far you zoom in to achieve good results. And they present a bunch of really cool applications. It's like a really fun paper. For example, a bunch of different shaders, path planning problem, and a knot tying animation. The goal in the task shown here is to build a texture shader that matches a 3D object to a 2D picture. And the idea is once you have a 3D object, you can then manipulate it. So now let's discuss some work that studies the correctness of taking derivatives of integrals. This very recent work by Wanyal et al. Provides an automated analysis that determines when applying the reparameterization trick is valid. This automatically identifies problems, including parametric discontinuities and other problems. In other words, you have some variational inference problem that you apply some analysis to, and it will tell you if parametric discontinuities will be a problem for you, rather than resolving it. But I guess the bigger picture that I'm imagining here is being able to know when there are problems automatically, and also to be able to resolve some of them automatically. Another recent paper, ADEV, studies differentiation of expected values of probabilistic programs. They provide an interface for composing derivative estimators while guaranteeing correctness of the whole system. So once again, I'm looking forward to speaking with any and all of you about any problems like this that you encounter in your research. And I'm happy to answer any questions. Thank you.
OK, are there any questions?
So question about the integration of the delta function stuff. So the very generalized form of this, right, is if you integrate a delta function of some inner expression, then you need to solve for all the zeros and then sort of add up the evaluation at that 0 point, which obviously solving for zeros generally of a function is a very, very hard problem. So I'm wondering if you have a specific sort of subset of expressions that you permit in terms of the integration of the delta functions that allow you to do this, and also if there's any possibility for whatever that subset is of either generalizing past it, or if it has to be that given subset.
Yeah. OK, that's an awesome question. So first of all, like the early works in this, so this is like talking about direct methods, right? So the early works limited themselves to affine discontinuities and sort of inverting, doing lots of things with affine discontinuities, not so hard. And so that's the expression that would end up in the delta. So that's how they resolved that. In our work, we worked with invertible functions. And we sort of had two different approaches. One was pattern matching. So we'd build these little grammars of expressions like affine functions, but also some more interesting quadratic or functions like that. And then we'd, once you pattern match, be able to have a hand-coded inverse that we'd use to get those zeros. We also had sort of a escape hatch that was like, hey, if you want to use a tricky discontinuity, give us the function as well as its inverse. And then we'll be able to do the sampling correctly. There's a question of, is invertibility sort of the best we can do? And the answer is no, we can probably do a bit better. The idea is all you really need is like the preimage. So as long as somehow you can figure out how to sample that zero set, you can do it. But coming up with the right primitives and having them all compose nicely is tricky, and I think an open research problem that's very interesting. Did that answer your question?